Hello and welcome to this Chemistry World webinar, Accelerating Materials Discovery with HPC and AI. I'm Natalie Starkey, Chemistry World's science media producer, and I'm here with you for the next hour. Now today we'll be hearing from Dr. Nathan Baker, who is the product leader of Azure Quantum Elements at Microsoft. Previously, he was a laboratory fellow in the Physical and Computational Sciences Directorate at Pacific Northwest National Laboratory, as well as an associate professor of biochemistry and molecular biophysics at Washington University in St. Louis. Dr. Baker is a member of the Washington State Academy of Sciences, a fellow of the American Association for the Advancement of Science, and a former Alfred P. Sloan Research Fellow. In this presentation, Dr. Baker will share some of Microsoft's latest updates, including how a collaboration with Pacific Northwest National Laboratory is demonstrating methods to accelerate scientific discovery for energy storage solutions. Together, the teams have been able to discover and synthesize a material that shows potential for resource-efficient batteries in less than 9 months. The presentation you'll hear today will explore how advancements in HPC and AI are accelerating the next frontier of scientific breakthroughs, in turn compressing the next 250 years of chemistry into the next 25. Now, a really great thing about Chemistry World webinars is that they're interactive, which means you can ask questions about any aspect of what Nathan covers today. We love to hear from our audience, and Nathan's getting ready to answer any questions you have. We also have some of Nathan's colleagues from Microsoft in the background helping out with questions today alongside the Chemistry World team, so do get your questions to us as soon as you can. We'll also be asking you to participate in some polls today. These are just for a bit of fun, but it's nice to hear from you in that way as well. So look out for those during Nathan's presentation, and you should be able to click on your screen when we launch those in order to add your response. But to post a question to us, then just look in the GoToWebinar panel for the questions box, and you can use that whenever a question springs to mind. You won't usually be able to see other people's questions in there, but myself and the team can, and I'll read them out towards the end of the webinar for Nathan to answer. But without further ado, I'm going to hand over to Nathan to begin his presentation. There we go, and I can see that as well. So I'll hand over and let you begin. I'll see you for some polls soon.
Okay, thank you. Well, first, I'd like to start by thanking the Chemistry World team for hosting this webinar and for all of you for attending. I'm excited to tell you about how we're using Azure Quantum Elements to accelerate materials discovery, how HPC and AI have really transformed the way that we can find new electrolyte materials. So first, I want to start with our interest in this space. So why does Microsoft care about the space of chemistry and material science? Well, there's a few reasons, but first is just the breadth of its impact. When you think about the best-in-class HPC capabilities that are available in Azure, you think about the leadership position that Microsoft's taken in artificial intelligence, and then you think about the space, well, how can that have the biggest impact? When you look at the space of manufactured goods, 96% of them have their roots in chemistry and material science research. So it's really hard to think of a bigger space with a broader impact for this technology than chemistry and material science. But in addition to its broad impact, it has a tremendous societal impact. When we look at the challenges facing the planet, whether it's clean water and sanitation, it's food scarcity, it's disease, it's affordable clean energy, all of those problems have the most likely solutions in chemistry and material science. So not only is there a tremendous opportunity for innovation in changing the way we manufacture goods, but there's also a tremendous opportunity for a positive impact on humanity and on the planet. So I can't think of better reasons for us to be focused on applying these technologies to the space of chemistry and material science. So we're going to start with one of our first polls, and that's just getting a feel for who's in the audience. And we'd like to know what industry you're interested in for these types of applications.
So we've got a number of options. So you've got manufacturing, energy and environment, healthcare and life sciences, consumer goods, or academia. Okay, we've got two options that are, that one's just edging ahead. Academia is edging ahead at the moment, but only just. I love watching these polls. It's like a horse race for me because I get to see all the results coming in. Okay, I think we'll stop the poll there. We've had a good amount of the audience voting. We'll bring up the results because it's always fun to see what everyone said. So yes, oh look, academia and energy environment were level pegging there. Is that a surprise to you, Nathan?
No, this is great. I mean, basic research always is the engine for the innovation in chemistry and material science, and of course, academia is one of the places where that happens. But it's great to see as well a lot of people thinking about the impact this is going to make on problems in energy and the environment. So, thank you to everyone who responded to the poll. It's great to get a feel for who's in the audience and what they're interested in. So, so maybe I'll move along here. There we go, and click over to what does this all mean? So when we thought about the urgency of problems, facing the planet, when we thought about the opportunity for accelerating the pace of research, I think our CEO summed it up best. Satya said, well, it sounds like our goal is to compress 250 years of chemistry down into 25. We don't have time to wait for the usual pace of innovation to address the problems facing our planet. So we need to hurry up. We need an order of magnitude improvement in the pace of innovation in this space. So we've taken that as our team's mandate. The whole point of our Azure Quantum Elements effort is to enable that acceleration through high performance computing and artificial intelligence. And the results we want to tell you about today is how we use that in collaboration with Pacific Northwest National Lab to go from simulation, which already saw an order of magnitude. We took 20 years worth of simulation, compressed it down to 80 hours, and how we went from those simulation results to full synthesis of a new viable material that has a potential for helping out with solid state batteries. And we did that in less than 9 months. So I want to tell you, give you the proof points behind that acceleration. But in order to enable that acceleration, we need to change the way we do our research. And in particular, we need to think about a paradigm shift. Instead of putting the burden of discovery and the burden of research on the slow process of wet lab experimentation, we should be reserving those steps for the most important and the most promising candidates in the discovery process. We should let computation shoulder more of the burden for discovery and empower those teams to go first to a computer, get leads from a computer, and then take those leads and refine them through wet lab experimentation. Experimentation isn't going away, it's just being accelerated by computation, and in particular being accelerated by high performance computing and artificial intelligence. So we've got our next poll here, and that's asking how your organization is using computational chemistry or material science tools for your problem space.
Okay, brilliant. And there it is on screen. So we've got a number of options. Maybe it's not applicable to you, that's absolutely fine. But yes, you might be heavily using computational tools, or you might just be getting started, or you might be considering it at the moment, but not actually using anything. So let us know your thoughts on this one. Oh, it's looking good. We're currently very heavily skewed towards the first option. So a lot of people, yes, heavily using such computational tools, but now it's balancing out a bit. That was interesting. Oh goodness, we are level pegging on nearly all of them at the minute. That's very interesting. Well, let's close the poll now. I think most people have had a chance, and we'll bring up the results. I think that's very cool. Equally spread, I would say, across all of those options.
Oh, that's very interesting. Yeah, thanks again to everyone who responded. It's fun to see the maximum entropy approach in the poll results here, where we've got a little bit of everything participating. So very interesting, and thanks for sharing. So we'll switch back over to the slides here and talk a little bit about first the platform or the technology we're using to drive this acceleration. So as I mentioned, we launched Azure Quantum Elements to enable the use of AI and HPC to accelerate scientific discovery with a specific focus to chemistry and the material sciences, problems that involve atoms and molecules. It launched last June. It's in private preview. We've had a lot of excitement with the results that our customers have gotten from the platform so far, as well as some of the things that, like the story I'll tell you today about the electrolyte discovery. So our approach to accelerating scientific discovery is to use a combination of techniques to address 4 key challenges. So the techniques I've already mentioned: high performance computing and artificial intelligence are tools that are available today to accelerate scientific discovery, and they form the backbone of the platform today. Those are the capabilities we used to do the materials discovery process and to reduce 20 years of simulation down to about a week. We also have built the platform with quantum computing in mind. Our project, our team sits in the part of Microsoft that's developing a quantum supercomputer, and we're building this as an on-ramp. When useful, practical quantum computers become available and they can be used to accelerate calculations for the most difficult chemical systems, and in particular to improve the accuracy, we want this platform to be ready to host those calculations. So we're building it as an on-ramp to future quantum computing. So I mentioned that we built the platform to address challenges, and in particular, we're focused on the challenges that serve as barriers to that acceleration of scientific discovery. There's 3 technical challenges outlined up top. Scale. There's always a desire to look at a larger search space of, say, molecular or material candidates. There's always a need to simulate bigger systems. Speed, we're never moving quickly enough, whether it's the pace at which we screen candidates and go through a virtual screening experiment, or it's even the speed with which we perform individual simulations, and that can limit the ability to look at timescales relevant to particular physical phenomena. And then finally, accuracy. As I mentioned, there are some challenging electronic structure problems that quantum computers are going to be the key to addressing. And until we have quantum computers, there are some limitations in accuracy. Some of those limitations can be addressed with high performance computing, but accuracy is the challenge and the frontier that we're most excited about quantum computing unlocking. And then finally at the bottom, I have a different kind of challenge, and that's the challenge of bringing products or discovery to market faster. That's a challenge of productivity. And in this case, we're trying to remove barriers to being productive with computational tools. And that's the first challenge I'll talk about here. So with productivity, we've taken the complexity, also the powerful capabilities of high performance computing in the cloud, and bundled them into a platform. At the foundation of the platform is Azure High Performance Computing and the variety of very advanced CPU, GPU, networking, storage architectures that comprise Azure HPC. We've pre-configured those into a chemistry supercomputer, and then we've optimized on top of that workflows that include the most popular packages out there for chemistry and material science simulations. Then, as you'll see in the electrolyte story, we've taken pieces of the workflows that use those pipelines and those popular software packages, and we've accelerated them with artificial intelligence. So there's AI accelerators built into the system. Together, this is bundled into a chemistry supercomputer. It's very easy to deploy, gives you best-in-class HPC capabilities, gives you the packages that you know and love and are familiar with using for your research, and then accelerates discovery with those packages through artificial intelligence. So we'll do our next poll here and try to find out from you all what application area or scenario are you most interested in for technologies like these?
Brilliant, there we go. We've got 4 options, and then the 5th option is actually other. And so if you wanted to let us know if there's another application area or scenario you're interested in, then please use the questions box. That's the best way to contact us. It doesn't have to be a question. You can just put a comment and let us know what your other is. We can come back to those later, so you can have a little think. Just let us know which poll you were answering. This is poll number 3. But otherwise, you can click one of the 4 options. And we've got lots of answers coming in, and we've got quite a few others. So I'm hoping to see some things in the chat. Okay, I think we've had a good number of people voting on that poll. So we'll bring up the results now. There we go. So materials discovery seems, nearly half the audience there. Again, is that a surprise to you? I expect not.
No, that's the story we're telling today. So that's great news. But I am excited to see other interests reflected here as well. I mean, the platform's very diverse. It can be used for a wide range of applications. Like I said, we're really interested in anything that involves atoms, molecules, and the computational tools that we use to accelerate those. So it's great to see the diversity of interests.
And we've had somebody already say electrical engineering and design optimization in the chat. So we've got another, that was their other. So yeah, there may be some more coming in. I'll let you continue with the presentation.
Okay, thank you, Natalie. So let's go back to that first challenge I mentioned of productivity and removing barriers to using computational tools. So as you know, Microsoft has invested heavily in Copilot technology, and we brought that technology to bear on the computational chemistry and material science space. And it has a few different forms. The first form is shown here in the little animation. This is an example of a capability that's actually available at quantum.microsoft.com for free. And the goal was originally for us to test and provide a demonstration of how the power of LLMs, large language models, can be used to do information retrieval in scientific spaces like chemistry and material science, where there is no tolerance for hallucination. So we do that through grounding. That's probably content for another full talk. But you can see some of the examples here of using this for information retrieval, and you can try it out yourself at quantum.microsoft.com. But that's just the tip of the iceberg of what copilots can offer. And so what I want to show in the next few slides is how we've integrated this into the process of performing calculations themselves, how we can use copilots to compose workflows of complicated steps, how we can remove barriers for learning new languages, new workflow managers, and then how we can configure, take the most complicated steps of syntax out of the problem and give scientists the answer. It's a copilot, it's not an autopilot. So what you'll see here is a set of videos with humans interacting with copilots and working together to solve a scientific problem. So this first screen just shows the interface that you first encounter when you log into the Elements platform. And we have a variety of tools deployed on the platform. The example we're going to show today is Quantum Espresso for a material science application. So hopefully it hits that target audience that we just saw in the poll. So we click on one of the tiles in the home page to launch Quantum Espresso to do a calculation for looking at the properties of a material. The first thing we're presented with is just a set of choices. There's default choices selected, but it says what type of virtual machine would you like to use for this calculation? We're going to run it interactively. And how long do you want the virtual machine to run? Nice thing about the cloud is if you're not using a machine, it does not need to be powered up. You start the virtual machine to do the calculation. So we start that here, it goes into the queue. After a bit of time, it becomes allocated and ready to use. So we go in and log into the node. Now, our experience with the virtual machine node is a Jupyter notebook, and I think that should be familiar to many of you in the audience. Jupyter notebooks have become a common tool for reproducible and interactive science. Nice thing about the Jupyter Lab environment is if you're old school like me, you can also drop down to a shell and use VI to figure out things, but you miss a lot of capabilities that are available through the notebook, including this % syntax you see on the screen here. So the first thing we're demonstrating is that information retrieval process. We use % chat, it's called a Jupyter Cell Magic, to interact with the copilot and ask questions. The first question is a scientific question. I wanted to learn something about indium arsenide, so I asked the copilot for help. It says, well, indium arsenide is an interesting semiconductor material. Here's the band gap. Here's some other things to know about it. And that got my interest. I now want to understand, okay, well, let's look at the band structure of the material. I want to explore the band gap in a little more depth. What packages can I use? It's my second question to the copilot here, and it tells me what's available on the system to start to answer some of these questions computationally. So next I go in and ask for some help. So as many of you know, the starting point for almost any calculation is a structure. And sometimes finding and building that structure can be the hardest part. So I asked the copilot for help. Can you help me generate some code for the Quantum Espresso system? And in particular, I asked for the ASE environment to generate a structure of indium arsenide. So it generated the crystal structure. That looks reasonable to me. So I'm going to go on to the next step. I'm going to ask for now some code that actually does the calculation I came here to do. I have the structure. I need help using Quantum Espresso to calculate the band gap and other aspects of the electronic band structure of the material. So our primary workflow manager on Elements is AIDA. We support other workflows as well, like Fireworks, but the one shown here in the Copilot used AIDA to go and build a workflow to do the band structure calculation. It pre-configured it. It pulled in information from the previous step where it built out the structure, and it went and ran the calculation. So I can go in and pull up the result. It generates a plot of the band structure, and it actually shows me what it did behind the scenes. And this is an interesting illustration of why workflow tools like AIDA are so powerful, because as you can see, there's a huge number of inputs. Those are the green circles that go into a very large number of calculations, the orange boxes, and actually trigger a set of decision points that scientists would have to run manually if they weren't doing this through a workflow package. So overall, the purpose of this was to show you how Azure Quantum Elements, particularly with tools like Copilot, running workflow engines like AIDA, can help remove barriers to getting work done to running these computational workloads. So time for another poll. And in this case, we're going to ask you to reply in the chat. And so we'll pause for a bit for you to enter some answers, and then I'll proceed with the presentation and we can look at the results later. But the question is, are you using any AI companion tools like Copilot to increase productivity in your research? And if you are, we'd love to know which ones and a little bit about your experience with them. Are they helping you out? Are they removing these barriers to productivity like we hope? So I'll pause for a second for a few responses, and then I'll just move on with the presentation.
Brilliant. I think that's a good idea. We'll give people a little bit of time to think about that one. But yes, do put your responses into the questions box. But equally, if you have any questions for Nathan, then you can put those in the box as well. And the Microsoft team are there to help me figure out which ones I'm going to put to Nathan, because if we get lots and lots of questions, we may run out of time. But we are going to give you a way to contact Microsoft at the end of the webinar. So if there's anything you want to follow up on, there's going to be some links included. So you can definitely follow up with them afterwards. So we've got a few responses coming in. Somebody is saying Copilots and Scholar AI are a few. A few people are saying no, they're not using any at all. So that's what we've got so far. But I think probably we could move on with the presentation. Feel free to keep putting your responses in, and then we can always come back at the end if we've got some more when you finish presenting.
Awesome, thank you, Natalie. Okay, then I'm going to jump into the other barriers we're trying to address. I have one slide each for these that give a quick example of what we mean by the barrier and how we're addressing it. And then the remainder of the talk after that overview will focus on that materials discovery undertaking, where we use the platform sort of end to end. So the first one I touched on previously is scale. There has traditionally never been enough compute that you have access to screen all the materials you'd like to screen. One of the value of the cloud is being able to do that type of scaling, that elasticity. So you're scaling up to use computational resources when you need them, scaling back down when they're not being used. So what does that mean in practice? When we take that combination of Azure HPC, the ability to scale out very powerful VMs to do very complicated calculations in the cloud, and we combine that with the optimized workflows, kind of like the one I showed before, we're actually able to look at just orders of magnitude more candidates. This was an example of screening candidates for a specialty fluid. It involved a series of different electronic structure calculations. These are all physics-based calculations to get at different properties of the molecular candidates for the fluid. And this example just shows what happens when you optimize the underlying codes for different CPU and GPU architectures and then scale it out using the power of Azure HPC through the Elements platform. So it's a simple example, taking physics-based calculations and scaling them out, but it gives you a great example of how we can get that order of magnitude improvement in research productivity just by taking advantage of cloud environments, pre-configuring those environments, optimizing tools for them, and then allowing the researchers to focus on their research questions while taking advantage of the scale of the cloud. So that's a simple scale example. Next, I want to talk a little bit about speed. And as a reminder, the challenge here is that, we're never moving fast enough with scientific discovery, but also in some cases, our simulations, our individual simulations of these systems are too slow and therefore too short. And they're too short to capture the physical phenomena we might be most interested in the system using a molecular dynamics simulation, for example. So I want to talk a little bit about how we're using AI in that case. So many of you, I'm sure, are familiar with how AI can accelerate molecular dynamics through so-called machine learned force fields. We've been doing a lot of work building out machine learned force fields, building out better ways to train these force fields. hardening techniques in active learning molecular dynamics that have been pioneered by wonderful research in academia, and putting that all together into workflows that allow users to run something that would often be only the domain of an ab initio molecular dynamics, where you have to use something like density functional theory to get at a force or an energy at every time step, and replacing that with machine learned force field calls, which give you those force calculations with a speed up of up to 1,500 times. So that gives you throughput in the system that's 1,500 times faster by using machine learning instead of density functional theory at each step. Now, active learning gives you an interesting counterbalance to that. You may be worried that if you do this type of calculation and you encounter states in your system that you haven't seen in the training data, that you may lose accuracy in your force field. The active learning loop in this approach allows you to go back in and retrain on the fly so that you're always getting ab initio level accuracy while still taking advantage of that 1,500-fold acceleration in the process. So active learning is an exciting approach, again, being pioneered in academia, groups like the Kaczynski Lab. We're taking advantage of that type of architecture as well as developing our own and making it available to make this acceleration easy for users of the Azure Quantum Elements platform. And then the last challenge I want to talk about before we move on to the materials example is accuracy. So accuracy, as I mentioned, can be challenging because there are some electronic structure problems that are too complicated for classical computers to solve directly. And that's the domain where quantum computing can come in and really make a difference in chemistry by solving the problems that are not amenable to classical computation. Right now, when we encounter those problems, we have to make approximations. And in some cases, those approximations can really degrade the overall accuracy of our work. So that's what I want to talk about here. One of the first challenges, though, in understanding whether accuracy is an issue, understanding whether you have a system that requires a quantum computer, is looking at the set of correlated electrons in the molecular system. So in this case, we've taken an arginine molecule and tortured it, started to pull off two of the nitrogen groups. So you can think about it as dissociation. The reason we did that was to induce correlation in the molecule in our test case. So with this type of system, the set of entangled or correlated electrons forms what's called an active space. And what we built into the platform are tools to make it very, very easy to identify that active space, understand which orbitals might be entangled or correlated, and get a feeling for which parts of the molecule might be involved, but most importantly, what the size of that active space is. Because that set of entangled or correlated orbitals is the hard computational core of this calculation. And if the space gets too big, we may need to use a future quantum computer to solve it exactly. But that's not always the case. So after identifying the active space, the platform offers the user some choices. If the active space isn't too big, maybe up to 20, you can push it a little bit further, but about 20 orbitals, you can fire up a large memory Azure node with, say, 4 terabytes of memory on the Azure Quantum Elements platform and actually just solve the problem directly without any need for further approximation or for quantum computing for that sake. If you have a very small system and you're curious about how quantum computers work, there's another avenue you can pursue. You can go call some of the quantum computing endpoints on the system. You can perform calculations using real quantum hardware, or you can just simulate them and understand how they're going to work. And in the future, when quantum supercomputers become available, like the one Microsoft is building, you will be able to solve the problem directly on that quantum supercomputer without any need for approximation. So the goal here is to help scientists understand what the accuracy limitations might be in their system, understand if they're solvable today with large memory classical computing nodes, or get a feeling for how quantum computing will address these challenges in the future. So let's shift gears now and talk about what all this means in the real world, in practice. And this is the story of the work we did with Pacific Northwest National Lab to screen a very large number of electrolyte candidates and use that to come up with an actual synthesized material in a very short period of time, 9 months, from running the calculation to having a vial of the material in our hand to show in the lab. So first, I want to talk about the origins of this collaboration. We originally ran these pipelines internally just to test our own tools. We were really excited about what these machine learned force fields and what these large machine learning models for property prediction could do. And so we started to apply them just inside our own team to understand, could they allow us to accelerate the search for new materials? And we came up with some exciting answers pretty quickly and realized we need help from the experts. We're based in Redmond, Washington. That's on the west side of the state. We turned to our friends on the east side of the state at a Department of Energy national lab, Pacific Northwest National Lab. That's often colloquially referred to as the chemistry lab because of its deep expertise in basic research in chemistry and material science, and its leadership in applying these skills for basic research questions on things like battery materials. So the next video is going to outline how this collaboration got started, what the vision was for it on both sides, Microsoft and PNNL, Pacific Northwest National Lab. And then we'll dive into the details of the actual technical work that went on in the collaboration.
We're joining forces with Microsoft to explore this convergence of artificial intelligence, high-performance computing in the cloud. And this is a shift that the world of science hasn't seen since really the dawn of supercomputing. And for us, it's helping us tackle these challenges in chemistry and material science that are embedded in the search for new energy storage solutions that the world needs.
My name is Vijay Murugesan. I'm a material scientist here in Pacific Northwest National Lab. My research is mostly focused on designing next-generation battery materials. Electricity generation needs to be renewable energy, but the renewable energy is not constant. It's sporadic, right? There's a lot of rain, or there's no sun, a lot of winds. Battery gives you an opportunity to store energy in a compact way and deliver it whenever, however you want.
Microsoft was really excited to work deeply with an organization that has strong roots in chemistry, material science, and how those disciplines relate to sustainability. Our goal was to work with PNNL to take the burden of exploring vast chemical or material spaces. Computational tools allow us to put the emphasis in the most promising parts of that discovery process. That's going to require a new way of doing chemistry that's computation first. Our team discovered a new electrolyte that uses 70% less lithium than shown in other industry announcements, because it replaces part of it with the earth-abundant compound, sodium. Azure Quantum Elements accelerated the initial phase of the discovery process. It took what would have been 20 years of computation and compressed it down into 1 week to identify the most promising candidates for later exploration.
Battery has multiple components. You are trying to put completely different type of materials together, and then you are asking them to work together as a synergetically. One part of the battery is called the lithium ion. Lithium is fast, and its ability to move even within solids is what makes lithium more attractive. But lithium is not something that you can easily go and dig it up. It's only available in certain geopolitical places. What the scientists have been thinking about is that how can we make it to the next stage, right? Can we use something else that can work as good as lithium, but without the baggage of their environmental and safety issues?
Tackling this approach through the traditional trial and error method is simply too time-consuming. The ability to narrow down the playing field from millions of potential combinations of elements and structures to dozens in just months, something that would have taken decades. The acceleration aspect of this can't be understated. What we're most excited about at Pacific Northwest National Laboratory in this partnership with Microsoft is the opportunity to accelerate scientific discovery, not just in chemistry and material science. This is just where we're starting. When you think about the convergence of artificial intelligence models coupled with high-performance computing in the cloud, running alongside of co-pilots that are trained in specific scientific disciplines, and having all of that come to bear at the disposal of the individual researcher or the scientist, that's a paradigm shift.
We're very grateful to the expertise in the Department of Energy National Labs, in particular the close collaboration with Pacific Northwest National Lab that made this happen. Brian Abrahamson and BJ and others who have enabled the work and made it possible. So it's just been a great example of taking acceleration from a computer and translating it to reality, but focusing the experimental effort only on the most promising candidates. So as you heard in the video, the outcome of that work was taking 9 months to go from the top of a discovery funnel, which was very large, over 32 million candidates, screen them extraordinarily quickly using AI acceleration in HPC, down to a small set, starting with about 500,000 stable materials and then filtering further to identify good electrolyte materials, and coming up with a candidate synthesized and characterized by PNNL that used about 70% less lithium than some of the other leading candidates that were out there. So I want to talk a little bit about how that happened and walk you through the technical details. First, where did we start? Where did those 32.5 million materials come from? So it was a game of what if. We took about 200,000 known crystal structures, and we followed a playbook that I think is fairly standard in material science. We started to substitute in the atoms of those known crystal structures with new elements. So on the right here, we have an example, a pie chart of the distribution of structures that we sampled from. And on the left-hand side, you see a heat map that shows how we selected, where we selected more frequently different elements from the periodic table. We put those together, and from that came up with 32.5 million, again, what if scenarios. Are these actual materials? And then they went through a series of stages of screening. The first stage of screening relied primarily on AI inference, and it went through a few steps, but at the core was an enhanced version of M3GNet that our team has been working on. That's an artificial intelligence model that has two interesting capabilities. It's actually very powerful at property prediction, but it's a small enough model that it's fast enough that it can be used as well in simulation. So from the same model with slightly different training data, you can do property prediction of things like energies or of band gap or of redox potentials, but you can also use it for the fast force calls as a machine learning force field that can be used to accelerate simulation. So it actually touches on two of those key characteristics that I mentioned earlier. So what did we do with it? We went from 32.5 million what if scenarios down to about 500,000 materials, where by evaluating the energy of the what if speculative material and some of its nearby phases, we could say, is this thing going to stay intact, or is it going to decompose into some other materials? That was the first screen. That got us down to about 500,000 materials that were predicted to be stable by this AI model. Then we started to apply a series of additional filters about stability. In particular related to the electrochemical stability window, if you will. The first of those filters was band gap. You saw it earlier in the demo with the Copilot. In this case, we're predicting band gap with an AI model, and we're using it to set an upper limit of stability. Then we're going through and calculating something called a redox potential, using AI to infer that value to understand potential reactivity of the material with the anode and the cathode of the battery. Finally, we need to understand how well lithium can move around inside the material. This is actually a very challenging calculation. It's not something that we have an AI model that can predict directly right now. We need to use simulation. And in any case, there's value in these simulations because you can use them to understand the mechanisms of behavior in the model. That's where we used a machine learned force field to accelerate these simulations. And finally, we're able to down select to the 800 stable materials that also had good lithium mobility inside the material. At that point, we turned to the traditional tools. We are, at our core, chemists and material scientists who've used physics-based models for decades, sometimes 20 to 30 years of simulating using these physics-based models. Before we handed 800 materials to a lab, which is far too many to characterize and synthesize, we wanted to winnow the space down further. So we took those high fidelity but slower physics-based models, and we used the techniques I described earlier, Azure HPC, to run them at scale, taking advantage of state-of-the-art hardware, and run the types of simulations to reproduce the steps I described above. Understand phase stability, understand electrochemical stability, and understand mobility of things like lithium through the material, and that's the dynamic simulation you saw here. From that, we winnowed the space down from 800 materials down to 150 that passed the stringent criteria that we had applied in the physics-based simulations. And we were ready to start looking at the materials manually. And the exciting thing is when we looked at that set of 150, a few known good solid state conductors popped out already. There were already good known electrolyte materials in that set. And that basically allowed us to have the confidence that this pipeline was working. It got us very excited. And that's when we turned to PNNL, got advice from Carl Mueller and Vijay Murugesan to give us feedback. This came from our computer. What do you think? We're not necessarily synthetic material scientists or battery developers. Does this make sense to you? They also got excited and they gave us some additional feedback. They said, you know, if you actually want this to be a good solid state electrolyte, you need to take some other things into consideration. First, please don't use any elements that are necessarily more expensive than lithium. Let's make the battery affordable. Think about weight. Make sure you have good energy density in the material. And also think about mechanical properties. These materials need to be compressible so we can get them into form factors and get good contact with the electrodes so that they can actually work as batteries. We built a few more filters, both just standard filters for elements as well as AI filters, took that human input into consideration and handed PNNL a list. And from that, they quickly, again, 9 months, synthesized the material you see in a vial here, tested it, and put it into batteries that we could actually use, again, as a prototype to power small electrical devices. This was very exciting for us. So, sorry, I need my slides to synchronize here. So what did this look like? So let's dive into the material itself. This is a cartoon, but it shows the basic characteristics of what emerged from the candidate material. We didn't select for any of these structural or compositional properties. We only selected for the performance of the material. That filtering process drove the rest of the steps. So this shows that the material has built-in channels. And from the cartoon here, which is based on a molecular dynamics simulation, but kind of customized so it's a little more easy to view here, shows how that structure of the material gives way to the performance of moving lithium from place to place in the system. Of course, the actual work is a little bit more complicated. You can read more about it in the preprint we have online. PNNL synthesized a series of the materials, not just the one that we targeted. They showed how conductivity changed across that series, basically exploring the role of sodium substitution into lithium or lithium substitution into sodium structures, measured the conductivity across that. This is a good set of conductivities as a starting point for an electrolyte material. There's still work to be done in optimizing the material and the battery system as a whole, but it got us excited that we were on the right track. This is one of the example structures that PNNL synthesized. It has the key elements of the material. And of course, they used a variety of sophisticated techniques you can read about in that paper, like X-ray diffraction, like XPS, like other ways to get at the structure and elemental composition of the material. And there's a lot more details in the paper. Ultimately, we got to a point where I think we have an exciting lead compound. As you saw with the clock, this lead compound's already powerful enough to do simple things and use it as a battery. The fact that it can be pressed into coin cells is exciting. It means we can start to do real world things with it now, but it's a starting point. The conductivity is good as a starting point. The overall system needs to be optimized, and there's a lot more work to be done. But we're just excited about the discovery process to date. We took 20 years of computation. That's how long it would have taken to screen the 32.5 million materials using traditional physics-based calculations. And because of AI, we were able to distill those down to a small number of compounds that we could give to PNNL. And instead of spending 20 years for that distillation process, we were able to do that filtering in less than a week. Once we turned it over to PNNL, they were extremely rapid about their turnaround and synthesized the lead candidate and characterized it, and we end up with what we showed you here. So overall, this is a real world demonstration of how we're using AI and HPC on Azure Quantum Elements to accelerate scientific discovery. But for us, this is just the beginning. So as I mentioned at the start, some of the toughest challenges are in chemistry and material sciences, and hopefully we've proven to you today that there's a real opportunity to accelerate the rate with which we find solutions for those challenges using AI and HPC. We're continuing to innovate ourselves, but we're really excited about seeing others, our customers, our collaborators start to use the platform and drive their own innovation and discovery. Not just in material science, we're seeing it with chemical examples. We've talked about Johnson Matthey and their work in the past. We have partners like 1910 that are using the platform for drug discovery. And I think the space it's boundless, right? 96% of manufactured goods is the domain in which this can have an impact. So I'll stop there. Very happy to answer questions. I do want to leave you with a few links where you can see a little bit more information about the blog. Read the preprint if you're interested in the technical details, and there's a little bit longer version of the video as well that you can view. So thank you very much for your attention and for attending the webinar, and I'm very happy to answer questions.
That's excellent. Thank you so much, Nathan. It's just brilliant to see that collaboration. You know, that it's just so much value there. And actually, one thing I'm thinking about, it really is just the start, isn't it? I'm wondering kind of what are the next steps for Microsoft and Pacific Northwest National Lab. It's always a mouthful to say that. And I know you're going to be working on other projects with them.
Right. So on the battery story, there's still work to be done, just understanding the mechanism, right? Getting into the details of, well, we ran this through a long series of filters that selected this material, but why is it a good material? How does it work? Those mechanistic details are key for understanding how to optimize it. So that's one line of work with PNNL. But PNNL and Microsoft made an announcement a few months ago that predates this one that talks about how they're using Azure Quantum Elements to make some of the tools that they've developed over decades more accessible to the scientific community, and basically taking some of these very powerful electronic structure calculation tools, making them available on the cloud through platforms like Azure Quantum Elements. And then we have our own, discovery adventures that we're going to pursue together. So please stay tuned, because I think this is just the start of some exciting announcements.
That's really good to know. Obviously, we asked the audience a little bit earlier what they're doing and what kind of work they're doing and interested in, but we're wondering what are the most popular uses that customers have for Azure Quantum Elements that you've kind of seen so far that can kind of spark people's ideas about what they might be able to do.
Yeah, absolutely. So it was actually nicely reflected in that poll you showed earlier. So, we think about Azure Quantum Elements is using AI and HPC to accelerate things that involve atoms, molecules, and simulations of those. So what does that mean in reality? We see lots of applications in catalysis. We see people using these systems to understand homogeneous catalysis, so things reacting in solution. They often use tools like AutoRxN. We have a blog post from a few months ago that shows how to scale out reaction network exploration using the cloud. We see heterogeneous catalysis applications, people using either just accelerated ab initio molecular dynamics simulations to look at reactions at surfaces, or in some cases starting to enhance those with machine learned force fields. We see companies and other customers using the platform for materials simulation. As I mentioned, we have partners now that are starting to use it to look at drug discovery applications. So the space is huge. And actually, sometimes the most fun is to see customers start to use the platform in ways you didn't expect and drive it with their own innovation using the tools we've developed.
Of course, yeah. You can't know everything, and actually it's when it goes out there you see what people can actually do and really the power of it. We've got a question from Christopher. What are the common barriers that prevent organizations from adopting HPC and AI tools to support their R&D activities? I don't know if you can shed some light on that.
Sure. Yeah, that's a great question. In fact, it's the things we tried to address first with the platform. So high performance computing can be challenging because it's cutting edge hardware. There's a huge variety of it. It involves not just specialized CPUs, but usually very specialized disks, file systems, low latency networks, and things like that. And then it changes very quickly because, as you know, the tech industry moves quickly and it's always updating the hardware. So one of the big challenges we've encountered with customers is just taking that diversity of hardware and simplifying it. Here's what you need, and here's how to configure it to have access to the best hardware to solve your chemistry or materials problems. That's the first thing we do with the platform, is just pre-package those environments. but they're not static environments, right? Again, the hardware changes quickly. There's always exciting new things coming out. So when we optimize chemistry workloads on top of that hardware, we're keeping up with those hardware changes as well. That means the scientist doesn't have to worry about, well, my GPU, version changed, or my InfiniBand library is different. We've taken care of that complexity so that they can just focus on their science. So really, we're trying to remove some of the very HPC specific elements from the equation and give scientists the scale and access to the modern hardware without having to worry about all those details and the constant changes that accompany them.
Okay, thank you. We've had a question regarding which AI model you used for the screening speed up of the millions of candidates, because that's a really good question actually.
Yeah, so that's the enhanced version of M3GNet that I mentioned before. One of our team members, Chi Chen, published a blog a few months ago that describes more of the details of what went in to that acceleration. But the foundation was his work and his work with others at UC San Diego on M3GNet.
Okay, thank you. And another question from the audience. Thank you to everyone who's sending in questions. We're getting lots of them coming in, which is brilliant to see. Do you see access to cloud computing? Sorry, I've just lost my question. Here we go. Do you see access to cloud supercomputer time becoming a limiting factor in research in the same way that people have to queue for months to get time on a synchrotron at the moment?
Well, I hope not. I mean, at a minimum, the elasticity of the cloud, the scalability of the cloud should make it easier to get time on cloud-based supercomputers than, say, on their on-prem counterparts. And that's important. In fact, cloud-based supercomputers are becoming comparable to some of the most powerful on-premises traditional HPC supercomputing centers. But as anyone who's logged into one of those centers knows, there's a long queue time, right? It often takes, maybe not as long as waiting for time on a beamline, but it often takes a while to get your jobs into the queue, and that limits throughput. So one of the things we're excited about by offering this cloud-based platform is that elasticity, that capability to get access to the HPC resources on demand because they're in a very scalable cloud environment.
Okay, that's good to know for the future. A question about which chemistry software programs you support. Are you able to just give a kind of quick rundown of some of those that you can support for chemistry?
Oh wow, how much time do we have left?
Give us your top five.
It's a long list. Well, and the other thing is I got to be careful. There's a lot of cool chemistry packages we support. I don't want to miss any by excluding them, but I think you can put them into basic buckets, right? So in molecular dynamics, we have, as I mentioned, ab initio molecular dynamics that can be run through a variety of codes. I'll talk about electronic structure in a second, as well as the traditional molecular dynamics workforce codes, GROMACS, NAMD, AMBER, LAMPS, and probably about 10 more that I'm forgetting. We have codes for electronic structure, both localized atomic orbital codes as well as plane wave codes for looking at materials. You think about those, we have NWChem and its counterpart ExaChem. That's one of the codes I mentioned before that PNNL's been developing. We have codes like ORCA, we have PySCF, we have VASP, we have Quantum Espresso, obviously. I used it in the demo. And again, probably a whole set that I'm forgetting. Beyond that, we also have codes for preparing structures. You saw ASE before for preparing material structures. There's a whole set of workflows associated with material simulations for building structures, taking subsets of the structures, manipulating it. So things like Atomate, things like PyMatGen, the Fireworks workflows, those are all available. And then we're starting to build out drug docking and other types of capabilities as well. So those tools exist on the platform and are usable by customers today, but we're actually rapidly expanding the space of those. So that's just a sample. Like I said, we probably would need another 10 minutes to go through all of them.
That sounds good. It sounds like there's a lot of flexibility there. That's good to know again. So we've had a question from our audience concerning how their data will be kept safe if using the AI tools, which is a great question.
No, that is a great question. Microsoft's been pretty clear about its privacy policies around AI. Your data is your data. So There's many ways that that people can use their data to train AI in Azure Quantum Elements. In all cases, the data remains yours. So if you go in and you run a simulation or you train one of these large-scale AI models, that becomes your model. Microsoft gives you an exclusive license to that model. We don't reuse your data. We don't reuse the associated weights. We've spent our own time pre-training many of those models. That's our investment. That's our stake in it. But the additional work you do training the model, the data you bring to it, that remains yours. Your data is safe. Your data sits in your own part of the Microsoft cloud where others don't have access. We're very serious about, privacy and data rights in the context of artificial intelligence.
Good, that is very good to hear. So I'm going to have this as the last question for today because we are running out of time. Somebody's interested to know what is included in Azure Quantum Elements. Are these same models and resources available for any new customer?
Right. So we try to get most customers up and running with just, kind of a crawl, walk, run strategy. So the first step is, customers get in there. They use workflows and tools they're already familiar with. That helps us understand, first how they can get started and get familiar with the environment. But also, are we missing any parts? We're in private preview. We are open to the fact that we don't have every software in the package on the platform. And there might be some optimization work that has to be done. So that's step one. The next step is to start to introduce some of the new tools that we've developed for things like reaction network exploration or some of the AI-based property prediction. And so we take multiple stages. And then the last would be to start to, help users customize those tools very specifically for those workloads. So kind of a crawl, walk, run strategy, starting out with, traditional simulation approaches and then building in different levels of AI acceleration.
Okay, thank you very much. I'm just going to let everybody know that this webinar has been recorded, and so we will get a copy of it posted very soon in the next few days. That will be emailed out to everyone who registered, and if you've got colleagues who would like to register, you can go to the Chemistry World page and they'll be sent an email when that is ready. So, no one's missing out. If you need to go back and watch anything again, then you'll be able to do that. You can also contact Microsoft. We put lots of links in the chat for you to have a look at. So there's lots of information there to follow up on, but I'm afraid that's all we have time for today. But thank you so much to Nathan and the Microsoft team for joining us today. That's been a really great talk. I think we've learned a lot there. And thank you to our audience. It's been brilliant in the questions box. We've had so much information coming in. So thank you for joining in the conversation there. If you missed anything today, of course, you're going to get the recording. And if you've enjoyed this webinar, then please check out chemistryworld.com/webinars for our future events. And while you're there, you might want to sign up for a Chemistry World account, where you can then choose to receive our very popular reaction newsletter that includes a weekly digest from big stories from across the world of chemistry. But from everyone here at Chemistry World, we look forward to seeing you again in a future Chemistry World webinar. Thank you.